tutorial, I'm going to show you how to run an exploratory factor analysis in R. And in an earlier tutorial, I already talked and introduced some basic assumptions of test theory, and then explained how to run a confirmatory factor analysis using Lavaan in R. So this tutorial builds on this earlier one. So if you haven't seen or worked through that one, I definitely suggest to go through that particular tutorial first, and then we can you can continue with this particular tutorial. Now, it's again about test theory. It's again about how to measure certain variables, and it's again that we are talking about latent variables and how certain manifest indicators measure these latent variables. In most cases where theory informs us about how a latent concept should be measured and what dimensionality we should expect, using a confirmatory factor analysis is actually the best choice. If we have theory, we can specify a model that aligns with that theory and then tests how well it fits the data. But there's at least two situations in which we may not be sure how the measurement model should be specified. So first one could be that we want to develop a new scale for a certain latent concept. Think about, for example, something like literacy. And we have, perhaps based on literature reviews or expert opinions, created a quite large item pool that includes what we believe are all aspects that are relevant to measuring this concept. The problem is we assume that all of these items should somehow measure literacy, but what we don't know if there are any subdimensions that we should account for. This is the first and perhaps the most often situation. Secondly, we may have tested a unidimensional confirmatory model, but it does not fit the data well. And we assume that perhaps the reason for that is that there may be more dimensions hidden in the item pool than just this one latent factor. In both of these cases, we may use an exploratory factor analysis to find out if there are any further dimensions in the data. So this is the major difference between exploratory and confirmatory factor analysis. In confirmatory factor analysis, we have assumptions about how the dimensionality of a certain concept should look like, and we can model based on our assumptions. In exploratory factor analysis, we have no idea about whether there are any factors, dimensions in the item pool, and we want to figure out what these may be. Now, for this reason, an exploratory factor analysis is very similar to unsupervised machine learning, where we also don't really know what the underlying dimensions are, or for example, if you consider something like topic modeling, what the topics are in a certain, for example, text corpus. So exploratory factor analysis also reduces sort of a lot of information to more general factors. So if we think about the goals of exploratory factor analysis, it's effectively an approach to detect structure in data. Here, the main goal is to identify one or perhaps also several latent variables that explain what we call common variance between several indicator variables. So often the goal is also to reduce several items to a number of overarching factors, and the way that we do this is to transform the covariance or correlation matrix in a way that represents a so-called factor structure. And this factor solution should at best have a simple structure, which means that each indicator, so for example, each of our items in a questionnaire, loads onto just one factor. Now, practically, there will always be cross-loadings, so an item may not only load on one factor, but also a little bit on another factor. But we hope that through this factor analysis, we find a solution where this item loads primarily on one factor and only minimally on another one. In an exploratory factor analysis, we always follow a couple of steps. So first, we check whether our items are appropriate for conducting an exploratory factor analysis. This is in some ways similar to a confirmatory factor analysis. So we test for whether the items are normally distributed. But we also have a couple of other tests that tell us something about the adequacy of our items for conducting exploratory factor analysis. Then we have to decide on a specific extraction method, and most importantly, identify the appropriate number of factors that we believe are in the item pool. Then we have to decide on a particular rotation methods and run the actual factor analysis, and then we finally assess the resulting model based on model fit, factor loadings, reliability, and validity. Now, to conduct a exploratory factor analysis in R, we do not have to use a package such as Lavan. We can actually use the package psych, which we already used to assess individual items, because it contains several useful functions to run exploratory factor analysis. Opened up R, and I'm actually going to create a new script here as well. We're just going to start on a blank slate, and the first thing that I'm going to do is loading some packages. As I said, we're always going to use the tidyverse for data wrangling, but primarily we are going to use functions from the psych package that we already learned about in the CFA session. And again, the first goal is to get some data, and I'm actually going to use the exact same data set that is included in psych package that I already used in the CFA tutorial. It's the data set that includes 25 items that should assess the Big Five personality model. But bear in mind, when we did the CFA, in line with the theory, it just didn't fit the data that well. So perhaps we can find out some further dimensions here. Now I'm actually going to use this entire code that is already a little bit pre-formatted to load, as well as already transform the data in a little bit. I'm calling the data by just using the function BFI. I'm directly transforming it into a tibble. I'm selecting only the variables that are of interest for us. So all items in the 25 item pool. I'm actually directly gonna remove all missing values. It's not many, so I'll just remove them to have a complete data set. And I'm directly recoding all the inversely formulated items with the same approach that I already talked about in the CFA tutorial. Again, I'm just subtracting all answer options plus 1. So in this case, the items are range from 1 to 6. So subtracting 7 will produce already an inverse version, but negative, of the item. And then I'll just multiply by -1 again to just inverse these items. So if I run this, and we can quickly check out how our data set looks like, we get an item and data set, or a tibble in this case, that consists of 2,436 observations, 25 variables, and again, these are items that measure the Big Five personality inventory. So we have 5 items for agreeableness, 5 items for conscientiousness, and 5 items for extroversion, neuroticism, and openness. Again, if you want to learn more about this data set, you can always run the help function, and it will get you a documentation about this particular data set, and most importantly also the different item formulations. Again, also in exploratory factor analysis, it's always important to not just look at the statistics, but also look at the items at the same time to see whether some of the decisions that we may take based on the statistics also make sense theoretically. Now, in a first step, as I said before, we need to check the adequacy of the items for the factor analysis. And traditionally, we run a couple of tests. In the first one, we can use a so-called measure of sampling adequacy test that has also been known or become known as the Kaiser-Meyer-Okin index. So in very basic terms, this is a statistic. It is a measure of the proportion of variance among variables that might be common variance. So the lower this proportion, the higher the KMO value, and the more suited the data is for the analysis. So we will actually get a estimate for the entire item pool, but also for every individual item. And Kaiser had actually quite a flamboyant style in describing thresholds for this particular measure. So he suggested, for example, that a KMO above 0.9 is marvelous, above 80 is meretricious, and the 70s middling, and the 60s mediocre, and 50s miserable, and below 5 completely unacceptable. So we can indeed run these tests in R using a function from the psych package. It's actually just called KMO, and if we just provide our items here, we get the following result here. As you can see, we get an overall MSA, and it's 0.85, so it's actually pretty good based on Kaiser's thresholds, and we also get the MSA for all of our items. And as you can see, all of them are actually pretty good. There's one item here that only has 0.75, which means that it doesn't share as much common variance with any of the other variables. But overall, this is a pretty good result that we can work with. Now, there's actually another test that also is quite known and used to assess the adequacy of these items for factor analysis, and it's the Bartlett test. So this one compares the correlation matrix to a identity matrix, which is basically just a matrix of zeros. So compares whether there's correlations between variables versus not at all any correlations in the variables. So the null hypothesis here is that the matrix is equivalent to the identity matrix. So it lets us in a way rule out that the variables in the dataset are essentially completely uncorrelated. Now the Bartlett's test is perhaps not that meaningful here, because in most cases, if we assume that there is hidden factors, it will always tell us that it is meaningful to conduct any sort of factor analysis. But because it's also included in a psych package, let's have a look at it. It's again a comparatively simple function, which is called core test.bartlett. And again, we just provide our items, not very complicated. And as you can see, it is significant. It's a simple chi-square test here telling us that the correlation matrix between these items is significantly different from a matrix that essentially is completely uncorrelated. So based on these two tests, we can assume, and that's why we do them up front, that it's meaningful to conduct a exploratory factor analysis, because a lot of the items are correlated in one way or the other. Now, it's very similarly to some of the preparations that we've conducted when doing a confirmatory factor analysis. We also should look at the items individually, and we can do two things here. So in the first one, we look at the psychometric properties of our variables. Again, we can use the describe function from the psych package that is very easy to use, but at the same time provides a nice summary for all of our items. So if I run this, we again get this nicely formatted table where we see the mean and standard deviation for all items, min, max, median, and stuff like that. But most importantly, again, skewness and kurtosis. And as we already established in the earlier tutorial, you can see that there's a couple of items that have a slightly larger skew than others, particularly O4 and A2 have a little bit more. Again, this should not be too problematic, but it's definitely something that we should keep in mind also for later, perhaps, decisions on which items to remove if we want to try to improve the model. Also here we can use the Madia test again for multivariate normally distribution. Again, we're not going to use the plot. And we've run this already in the earlier tutorial, and again, it shows us that this violation is actually violated. And this is actually in so far interesting to us. There's different methods in how we can do an exploratory factor analysis. So as I will explain later, there's principal access factoring, but also maximum likelihood. And principal access factoring can deal better with data where this particular assumption is violated. So we should, later on, perhaps should rather use principal access factoring and not maximum likelihood. One last thing that I find that I think is important to mention, instead of these tests here, we can also look at the correlation matrix itself. That's of course perhaps one of the easiest ways in which we can assess whether at all it is meaningful to conduct a factor analysis. And one easy way to produce a correlation matrix in R is using the tidyverse here, is by just simply calling our items, selecting the ones that we want to explore. I'm actually only going to select all items from the agreeableness subdimension, and then just simply use the function core. And this will actually produce already the correlation matrix, but I'm also rounding all of the items to 3 points. Otherwise, it looks just a little bit, it's hard to read. So if I run this, and get a very simple correlation matrix that tells us here, for example, that the first item is moderately correlated to all the others. And this way we can also see, of course, that, a lot of these items are correlated, and therefore it makes perhaps sense to have a look at them. There's actually a nice package called CorePlot, which we can use after we've created such a correlation matrix to plot a somewhat nice matrix with colors that can help us a little bit more to assess correlations between these variables. So if I run this particular code here, we get the following matrix. And as you can see, this helps again also to assess correlations also visually. There's various different ways on how we could visualize this. We can of course also plot scatter plots between the individual items, but overall, yeah, if this is really dark blue, then there should be a good basis for conducting a factor analysis. Establish that our items are adequate for performing an exploratory factor analysis. Let's actually start to run it. And before I do so, I will also talk a little bit about some of the ideas of exploratory factor analysis. So generally, we distinguish three alternative approaches. The first one is principal component analysis, one that is very commonly used but also heavily criticized. Then secondly, principal axis factoring and maximum likelihood factor analysis. Now, the principal component analysis has been criticized a lot because it's not actually based on a reflective measurement model. Now, going back to some of the ideas of classical test theory, this means it does not assume that the variance of any measurement is composed of different elements, including the true score and the measurement error. It actually assumes that all variance in a manifest indicator is completely explainable by a common factor, which is an assumption that in practice doesn't really make that much sense. So the more used approaches or most used approaches to do an actual true exploratory factor analysis are hence principal axis factoring and maximum likelihood factor analysis. Both rests on the assumption as the confirmatory factor analysis that really align with classical test theory. So again, this means they decompose the variance of each measurement, and every observable measurement y, for example, an item in a survey or the response to an item in a survey, is composed of the variance explained by the latent variable, which we also call the true score. Then the variance explained by the specific indicator, which might be a smaller part, again a type of true score, but a different one. And then the measurement epsilon, or measurement error generally speaking. So similar to our tutorial on the confirmatory factor analysis, we can write this down in this formula. So y of a certain item, the measurement of a certain item, equals tau, the true score that is explained by the latent variable, tau A I call it here, and then tau B, which is the item-specific variance, and then of course the measurement error epsilon. So later on we will actually use principal axis factoring, but usually, and we'll use this because the Madia test was significant and telling us that the assumption of multivariate normal distribution was violated. But in practice, principal axis factoring and maximum likelihood factor analysis usually do not give us that different results, so we can actually run both and check out the differences. Now, a first step before we can actually run the actual analysis is we need to determine the number of factors, right? If we have an item pool of 25 items where we don't really know how many factors are included there, we need to find a good way to determine what is the right amount of factors. So unfortunately, there's no common approach or criterion that we can use for extracting factors. So very generally speaking, our decision should be based on both theoretical plausibility, right? For example, even if any of these approaches that I will talk about tell us that 10 factors would be the best solution, they may be theoretically completely impossible to interpret. So it's a combination of theoretical plausibility, but also then, of course, the reproducibility of the factors based on the correlation matrix. And for the latter here, there's a couple of approaches that are often used in the literature. Perhaps the one that is used the most, but again also quite criticized, is the analysis of eigenvalues, and then just using the so-called Kaiser criterion to determine what is the perfect amount of, or the appropriate amount of factors. I will show you how that looks like in a second. There's an alternative approach that has actually been considered to be the best option by many scholars. It's the so-called parallel analysis. But there's many more, including, for example, a very simple structure criterion, looking at the empirical BICs, the Bayesian information criterion, looking at root mean residual distributions and stuff like that. Now, here we will actually consider the first solution to look at the eigenvalues based on the Kaiser criterion as well as the parallel analysis, and then I will also show you a function that you can use to get some information about any of the other approaches. Now, traditionally, many scholars have determined the number of factors in a correlation matrix by examining the so-called scree plot of successive eigenvalues. Now, I don't want to go into the theoretical description and definition of eigenvalues because that is actually quite complicated. But using the scree plot is actually comparatively simple. So if there's sharp breaks in the plot, it will suggest the appropriate number of components or factors to extract. And we can actually use a very simple function that is called scree to produce such a plot. So let's actually have a look at that. So we are going to extract the appropriate number of factors, and the simplest version is scree BFI. Again, we just pass our items, and if I do this, I actually will get 2 lines here. I actually only want to have 1, so I can add a small comment that is PC equals false. We don't want to have the principal component eigenvalues. We want to have the factor only, so PC equals false. And then I'll get a very simple scree plot that looks like this. Now we already have a line drawn here at the 1, and this is actually the Kaiser criterion. So when this line here goes below 1, that is the amount of factors that, according to this criterion, is optimal. So it's 4, or perhaps a little bit better, 5. So from this point of view, you think that 4 or 5 is a good solution. Now, as I said before, this is not the best solution. There's another one called parallel analysis, which we can simply use with a function called parallel. Again, we just pass the items. Now here we actually have to say what exactly we want to do. So we have to say, we have to provide the method. So in this case, we want to use principal axis factoring. And we also need to show needs to tell the function which eigenvalues to show in this case, so the one from the factor analysis and not from the principal component analysis. This is why we add these particular arguments to the function. So that's what I'm going to do. And now I'm producing a plot. And actually there's also a output here in the console that we will look at later. I'm producing a plot that is actually very similar to the scree plot that we saw earlier, but there's a couple more things included. So this blue line is exactly the same as the one that we had before, and again the vertical black line tells us the Kaiser criterion. But now we also have a randomly sampled or simulated data set that is telling us how our actual empirical data compares to randomly simulated data. And according to the parallel analysis, where these 2 lines cross is also a good point for extracting the number of factors. So this one actually suggests 6 in this case rather than 5, and this is also the result that we get at the bottom here. So the parallel analysis suggests 6 items. Just to show you, there's another function called n factors that again just takes our items. If we run this, it's actually in factors. This actually takes a little bit of time, but then produces 4 different plots that relate to a lot of the different other approaches that we've talked about or that I mentioned. So the very simple structure here, it again seems to be 4 or 5, where a certain saturation is in the fit is reached. Complexity, of course, is another one that we can look at. Empirical BIC, again, we see that the number of factors or the empirical BIC doesn't get much lower once we reach 5. The root mean residual plot again tells us something that there's a little bit of a inflection point here at 5 or 6. So all of these solutions sort of suggest a similar amount of factors, but let's for the moment stay with the 6 factors proposed by the parallel analysis, and use that. Now bear in mind, this is a item set that should, in principle, measure 5 dimensions, and now the parallel analysis actually suggests 6, but as we've seen, some of the others also thought it would be rather 5. So we'll see how well a 6 factor solution actually makes sense, or whether we actually need to go down to 5. Now when we estimate the model, we can simply use a function that is called FA for factor analysis, very simple, where we need to specify the number of factors, what type of methods to use, and as a third option, what type of rotation method we want to use. Now, very generally speaking, rotation is again something that is quite complex to understand in detail, but very generally speaking, rotation minimizes the complexity of the factor loadings and makes the structure simpler to interpret. So there are generally 2 types of rotations. The first one is called orthogonal rotation, which constrains the factors, the resulting factors, to be uncorrelated. Now this is often favored, or actually used, but in many cases it's really unrealistic to expect that the factors are uncorrelated. Now in our case, we already know that personality traits are correlated based on our confirmatory factor analysis. So forcing them to be uncorrelated makes it less likely that the rotation produces a solution with a very simple structure where actually really one item is only loading on another. The alternative is so-called oblique rotation, and here we permit the factors to be correlated with one another. So often it produces solutions with indeed a simpler structure, and more importantly, it aligns more with the theory. So I would suggest to always use oblique rotations. We actually have a couple of different ones here. The one that I use most often is Promax. So let's quickly just copy paste this code here to actually run the analysis. And as you can see, we just pass this BFI items object to the FA function through the pipe. We are specifying 6 factors. The method is here principal axis factoring, and we rotate using a Promax rotation. Now I'm actually gonna save the results of this analysis in a fit object, because we can use the print function to customize our output a little. And this is really, really helpful in order to get a good and interpretable solution. So if we use print and then say the digits should all be rounded to 2, and we want to cut out any factor loadings that are below 0.3, bear in mind, a exploratory factor analysis always produces the factor loadings for all items on all factors, but we want to see whether there are particular items that belong to particular factors, so removing them is actually quite nice. In fact, actually, let's not remove them in the first case. Or actually, I'm just gonna hide this particular argument. You also want to sort. You will see later what that does, because that also helps to interpret. So let's actually run this analysis, and it actually produces a quite big output, of which the first one here is the most important one, because it's the so-called pattern matrix. Now here, because I removed this argument that actually hides factor loadings below 0.3, we see all of them. So for example, the item E2, which we know as extroversion, loads onto a first factor, which is actually not called in any way, it's just called principal axis factor 1, 0.75, and really, really low on all of the others. Right, so this is what the simple structure is trying to achieve. We want to have that items only load highly on one factor and not much on the others. Now, if I hide all of these low ones, so let's actually rerun it with this cut argument, it will look a little bit different, as you can see. Now we see clearly on which of the factors these items load highly, because all of the loadings below 0.3 are actually omitted. Now we can see that there's some items, for example this one, that load on 2 different factors. So this one loads on P1 and PA6, and as you can see, it loads actually negatively on PA6. But very roughly speaking, what we see here is what we potentially also would have expected, that all of the E items load onto one factor, all of the N items seem to load on one factor, and so on. So it seems that this exploratory factor analysis does indeed detect the factors that we would expect to be in this item pool. But we see also that there are some items that have, considerable cross-loadings here as well. This one doesn't seem to be a very good item. And there's also now the sixth factor here, which apparently, if you look at it, doesn't make that much sense. Right? It has very weird factor loadings for some items, but it doesn't make much sense. So one of the first things that we perhaps should do is rather re-estimate the model with only 5 factors, but as you can see, these 5 factors make theoretical sense. The sixth one does not. Before we do so, I just want to quickly have a look at these other columns that we have here. So we see there's an H2, a U2, and a com column. The first one is actually also known as communality, and it tells us how much of the variance in the item is explained by the particular factor. Right, as you can see here, 56% of the variance in E2 is actually explained by all of these together, but as we know that the factor loading is really high only on the first one, it's primarily this first one who explains this. Now U2 is just the inverse. It's also known as uniqueness. So it's just 1 minus H2. And the lower the value, the more unique the item. And the final one is COM, which is for Hoffman's index of complexity. And this is actually a nice index that we can also have a look at, because if it's close to 1, it means that this particular item is only explained by one factor. Right, as you can see, for the first one, this is really great. It's looking good. But for example, for this one, where we can also see where the problem lies, it's actually quite high. So this is just another way to assess our our solution that we have so far. But because we already know that the sixth factor here, at least theoretically, doesn't make much sense, how about we just rerun the exact analysis, but just with 5 factors. So as you can see, I just copy pasting the code. I'll perhaps change the fit object so that we don't override it. And I'll just rerun it with the exact same specification. And let's look at the results. Now we can see that the pattern matrix makes a lot of sense. There's still some cross-loadings here, but all of the expected items load onto the factor that we expected to load onto. Now bear in mind, the analysis only tells us which item have common variance. It doesn't tell us what these factors are. It just says PA2, PA1, and so on. So now we as a researcher have to dive into the item formulations and check which ones go together and make sense of it. Now, because this is the personal inventory, the big 5 personal inventory, we see already that all of the ones that we would expect to go together actually are going together. So potentially PA2 is neuroticism, PA1 is extraversion, PA3 is conscientiousness, PA5 is agreeableness, and PA4 is openness, right? But these labels we put on these solutions. It's not something that the analysis can actually tell us. There's another thing that is interesting now, because we've used a solution, a number of factors that was not proposed by the parallel analysis, the model fit is actually slightly worse, right? The Tucker-Lewis index before was above 0.9, I think 0.92, and now it's actually below. So we indeed reduced the model fit with this version, even though it theoretically makes a little bit more sense. Now the question is, of course, can we change even more? As I said, the results look much better, but there's still some cross-loading, so items with a comparatively high complexity, we may want to remove them as well. So I just actually remove them from the original item data set using this code, and then I'll actually rerun it again. So let's see whether that works better. I'm removing N4, E5, A5, A4, and O4. So if you just quickly look why, N4 I think is pretty clear. It is has a weird negative factor loading on PA1. Then I'm also removing E5. This is just because it has a comparatively high complexity. Then I'm also removing A5. A5 has also cross loadings quite a bit, and I'm O4. Yeah, this is just because it has a comparatively low factor loading overall. So once I've done that and I'm running the same analysis again over this new item pool, we'll again now get an almost, at least by the looks of it, a perfect solution where every item nicely loads onto just one factor, and as you can see, the commonality or the complexity also is much better. Now we would assume that this leads to a better model fit, but in this case actually it does not. It is slightly lower, but the ARM SAA is pretty good. So yeah, this is still again a model that can be improved. And if you remember from our confirmatory factor analysis, we sort of gotten to a very similar solution, which still didn't perfectly fit the data. So there's definitely some issues in this item pool that does not really make it adjustable to a 5-factor solution, but this is potentially the best we can do at this point. Now, with that said, we can actually use a function that is called FI diagram here, as you can see here, and it again has some interesting arguments that we can use to customize it. This is actually a function that produces a visualization of this solution. So we can quickly run it without any specifications. And as you can see, it creates this plot that looks very much like a reflective model. By default, it has suppressed some of these inter-item correlations, so we may want to change that. We can do that by first saying cut only ones that are below 0.1 perhaps, or even below 0.05. And I think I also added that the digits should be rounded to 2, not to 1. That way we can actually see the exact results. So if I rerun it, now we get all the path in this factor model, and we can see how they are correlated, and we can see all the factor loadings on these different variables. Now, if we are satisfied with this solution, we may want to, in the next step, very similar to the confirmatory factor analysis again, assess the reliability of the individual factors, right? And reliability in this case is again estimated based on various estimators such as Cronbach's alpha or McDonald's omega. Now, unfortunately, in the CFA session, we have seen that there's a nice function from a package called SEM-tools that actually extract these reliability estimates from the fitted model. As far as I know, this doesn't exist for a fitted model based on an exploratory factor analysis, so we actually have to do it manually. But this is, again, also not that complicated. It's all written down in this particular code. So if you copy-paste this, I'm only actually going to do this for the first factor, which I think is neuroticism. So it's based now on N1, N2, N3, and N4. So I'm going to create a new object that only contains these items. And then we can actually use a function omega, tell this omega function that this is just one factor. Right? It's the first one. So it's actually this one here, right, in our factor analysis diagram. And we don't really want to see the plot. So I'm actually saving, again, the results here. They're much more comprehensive. But now if we dig into this particular object, we can actually extract the alpha, which in this case is 0.799, so almost 0.8, pretty good. And the omega, McDonald's omega, is also 0.81, so even slightly bit better. There's also another function that we can wrap around this particular object, which is called simply alpha. And these produces quite a lot of information about Cronbach's alpha. So here's the actual alpha. We get confidence intervals. We get also some information if it can be improved if we would drop one of the items. So this is what you can see here, some raw statistics as well. So this is, of course, all very good information to explore reliability of these factors. I only here provided the example to do it for one, but we can now, of course, run it through all of the others as well. That was already the end of this particular tutorial. So I showed you how you can run exploratory factor analysis using the psych package in R. The important steps are testing the adequacy of your item pool for exploratory factor analysis. Then we need to extract the number of factors and decide on an extraction methods. Generally speaking, principal axis factoring is a good solution here, or a good option. To extract, we better use parallel analysis than any of the others, but we can play around a little bit with different solutions and check out which one theoretically is plausible. Then we actually estimate the factor analysis based on the solution of this extraction. For example, in our case, 6 or 5 factors. We look at the pattern matrix, try to make sense of the results, perhaps try to improve the final solution a little bit, and then also check out model fit as well as various reliability estimates. Again, Factor analysis, both confirmatory and exploratory, are complex subjects, and you may as well now dig deeper in classic books on test theory in order to understand it in its full complexity. But this should get you started, and it provides you with some code to play around with. So thanks a lot for listening, and goodbye.